To continue the last video, now I would like to show you the problem with constraints. So until now we just worked on the problem without constraints, so it was the Lagrange problem of optimal control. But now we have to focus on the problem with constraints. So the problem is containing constraints. This is going to lead us to the so-called Pontryagin Minimum Principle. So what is the problem now? The problem is more or less the same. Again, we have got a function denoted by j, which is the integral of the function v from time t1 to time instant t2. So we would like to minimize this cost. Second, we have got a condition, and this condition is a set of nonlinear ordinary differential equations. This is coming from the plant model, as in the last situation. And finally, we have got some constraints on the control signal u of t, and u of t must be in the set of u, the capital U, and this capital U denotes the set of admissible control. It's very, very important to see that our control signal must be in a set. We have to select our control from a set. So it's quite difficult to solve because the Euler-Lagrange equation and the variational principle results in unconstrained system. But now we have to solve the problem of constraint somehow. And this is why Pontryagin introduced the Hamiltonian function h, which is equal to v plus lambda transpose f. And I just copied the three equations from the last video, the set of equations for the state, the set of equations for the co-state, and finally the control equation dh over du is equal to 0. So let's move on to the last equation for a moment. If we calculate the dh over du and we set it to 0, equal to 0, we can get the optimal value of h. But in this case, we do not have any constraint for u. If we work on to minimize on the right, to minimize the Hamiltonian function h according to u, and u has no constraint, and we solve this minimization problem somehow, we can get u star. So we minimize h and we pull out the solution of u. This is the argument of u, and it will be u star. Okay, this is an unconstrained optimization problem. But now we have got constraints, so that's why this equation cannot be used anymore in this case. So dh over du equal to 0 is cannot be used because we have got constraints. The first equation, the state equation, and the second equation, the co-state equation, of course, can be used. They do not modify, but we have to do the minimization according to the set of admissible control. So we have to work out a technique which minimizes the function, the Hamiltonian h, but which take care into account the constraints. So u is equal, u is in the set of the admissible control, and we can get u star by the solution of this constraint optimization problem, constraint minimization problem. And this is the so-called Pontryagin minimum principle. And if we solve this constraint problem, we are going to get u star, and by the solution of the state and co-state equations, we can get x star and lambda star, of course. And the other expression of Pontryagin minimum principle is that the Hamiltonian function has a minimum at u star, and this is what I put to here, and it's very, very important that it's a constraint minimization problem. This is what we have to solve. Finally, There are many other ways of optimal control problems, but many of them is based on this Pontryagin minimum principle. So this Pontryagin minimum principle is a celebrated principle which is used in optimal control problems.